GPS navigation stands for Global Positioning System. So please write that down anytime you see the little pencil icon. And you see this little thing on the windshield there. That is a little GPS device. People used to buy those. Now it's on your phone. And there's a satellite. So nothing to write down here, but what I want to tell you, we're going to talk about this a little bit later as well, is that it is a cloud of 27 operational satellites. There's actually 32 as of June 2022, and you can check out those links if you want. But 27 of them are considered as operational at any given time to give accurate location. All the positions of the satellites are accurately known at any given time, which is really cool because they're traveling super fast around the Earth, and we know where they are at all times. And the GPS device receives a satellite signal with time sent information. Your GPS device might look something like this. Yes, that's a phone. And the device calculates the distance to the satellite, which is pretty amazing. And then it also gives the intersection point of multiple satellites to define the device location. That's what tells you where you are. So, how precise is it? Well, if you only have one satellite, it limits the possibility of anywhere around a sphere because it says you are this far away. So, I could be anywhere in the sphere and be that distance away, which might be, hundreds of miles. Okay. Well, if we have two satellites and the Earth would, of course, be somewhere in the middle of this, then it could be anywhere along this ring because that's the intersection of those two. So, what I want you to note down here is that three satellites limit the possible GPS receiver location to two spots. There's a little simplified diagram. Its location could be here or here. But the problem is one of those spots that these three spheres intersect is not on Earth. And that's this one that'd be out in space. So the software on your phone says, oh, well, if one of them is like way out in space, then it's got to be the one that's really close to where it thinks I am. And so that way, three satellites is really all you need to get a location. But four satellites will eliminate most errors. So that's what I want you to note down. Three satellites gives you a general location, and sometimes it can actually be accurate. But a fourth satellite, being able to see a fourth satellite at any given time, will eliminate most of your errors, and that definitely gives you a more accurate location. So there's this thing called geometric dilution of precision. That if you have these satellites and they're sort of at all these steep angles away from your phone, because of all these angles, you're getting a good GDOP and a pretty accurate location. Whereas if they're all directly overhead, then it gives you sort of a little more unknown, more uncertainty. And then of course you could have things in the way that block them, which really isn't four satellites. In this case, it's only two. But a good GDOP is satellites that are kind of all far away from each other, but that your phone or your device or whatever it is can actually see the position of. So another thing you're going to note down on this slide is make note of that 27 satellites. Okay, it's from the 32 total. It actually expanded from 24 in 2011. Now they have 27 active. So it just gives more accurate locations because at any given moment, you might have those four satellites available instead of just three. So you would eliminate more errors. They're approximately 20,000 kilometers above Earth, or 12,500 miles. So they're really, really, really far away. One orbit takes 12 hours, and they're positioned in a way so that you have really good satellite coverage no matter where you are at any given point in the Earth. So it does cover the entire Earth. I'll leave that there if you want to pause that if you need to make note of these. And if you want to track them across the Earth, you see these little red stars. This would be where any one of the satellites is at any given moment. And this is how far it reaches latitude wise. So it's not actually going over the poles. Otherwise, these lines would be going up to 90 and down to negative 90. It only goes up to about 58 degrees, 55 degrees, somewhere around there. But there is one GPS satellite you can see that scoots up here a little bit further so that it gives a little bit of precision to a place here in Alaska. So that's so nice of them. So there's a little bit, it helps with satellite precision or GPS precision in Alaska. But other than that, you're getting most of the population that we care about in the US is going to be able to receive our precise location within this region. So that's by eliminating those far north and far south regions, we can have greater coverage in the areas that we actually care about. These satellites are for United States use. They are US GPS satellites. The European Union has different satellites that they use, and so on. So GPS accuracy. So how do you get accurate? Well, in 1993, it was accurate within 100 meters. That was because they had this thing called selective availability, and that reduced accuracy. It actually would have been more accurate, but the military said, "Hey, we're not sure if we want to trust people with knowing where they are." So they turned this thing on, and people could only figure out where they were within 100 meters. Well, that's not really that accurate, and certainly not accurate enough for military missions. If you wanted to bomb somebody or something like that, you're not going to hit your target. So that was really what they were thinking about at the time. Well, in 2000, then selective availability was removed. The president at that time said, "Hey, I think we're probably safe for the general public to have this." So then it was within 15 meters, or about 50 feet. And then a little bit later, then we had this thing called differential position, or GDPS. And that is global differential position. And it was really, really expensive. It required an additional receiver, but that allowed us to get up to 3 to 5 meters. Well, the problem was it was really expensive. So that wasn't really built into a lot of technology. Where now we have this thing for aircraft that is called the WAAS, WAAS, that allows for things less than 3 meters, or 10 feet, or less, actually much less. And so airplanes can actually use this with really high precision and high accuracy. But that doesn't really answer how we can use it when we're driving around. We'll get to that. So there's this thing called WAAS, and that is Wide Area Augmentation System. I absolutely want to make sure you know this. This is mostly used for aircrafts, and these are ground-based stations. So let's take a look at that here in a second. Where do you get errors from? Well, the reason that we have these errors, and I'll go back to this, where it says that it's within 3 to 5 meters, and so on, is because you have all of these errors that happen at different levels from the satellite all the way down to your receiver, that can add up to 10 meters of error. So if you can eliminate these errors, and a lot of these were software issues that computer engineers and software engineers were able to figure out and improve upon, and now that actually has gotten our precision much, much, much more precise, much less of an error. So things that we can do to increase GPS accuracy. Well, there was this thing called Global Differential GPS, GDGPS, which was expensive and is actually no longer in service. There's this wide area augmentation system that aircraft use, and is a ground-based system. There's also this thing called assisted GPS, which we use as cell phone towers now to give us accurate locations using our phones. So what that does is the GPS towers will target into our phone and bounce those signals also off of cell towers that are known locations. And because of that, it's kind of tracking both those at the same time. And so if we're not near a location of a cell tower, then the GPS can find the cell tower, beam that information up to us, and kind of give us a lot more accurate location, which is why we can use these things in our cars to tell where we're going. So GDGPS really accurately survey ground locations to correct using surveyed locations to correct these errors. It'll correct for increased accuracy, and it was within 10 centimeters, but it was really expensive. So if you want to note down what GDGPS is, it was up to 10 centimeter accuracy. Use a known base location. That is kind of the key for this, is that it used ground location. So make sure you note that, you highlight that. That's really how we get accurate GPS, is to bounce things off known locations. So the wide area augmentation system is largely used by aircraft. You see this neat little picture here, and there's the WAAS station down here. That is a known location, so the aircraft can use that, and it's operated by the FAA. And aircraft actually uses for all different phases of flight, and it is a very accurately surveyed ground location, once again, used to correct errors. The benefit of WAAS, it can be used as a primary means of navigation. You have direct routes, gives you vertical guidance so that you can know how far off the ground you are. It decommissions older equipment that really wasn't as accurate, and we talk about that when we talk about flight navigation. Those VOR systems, it helped to decommission some of those. It also simplified onboard equipment, because you just have this one piece of equipment, which is your GPS. So it gives increased air traffic capacity. More planes can fly and land because they can safely know their exact position. So the assisted GPS, this is the one that we end up using, is used with GPS capable cellular phones, which is pretty much all of them now. And it was developed by development was accelerated by the FCC 911 requirement to be able to make cell phone location data available to emergency call dispatchers. So they had to know where you were. If you had a cell phone, you called 911. So now they're using these assistance information from these base stations. So if you look at your phone, there's a base station which tracks to some known server. The GPS tracks to these servers. It also gets signals from the GPS satellite. So that goes to a receiver, to these servers, to the cell towers, to our phone. The satellites go to our phone. And because of both of those, we're getting very, very, very accurate locations. Now, it does work by providing necessary data to the device via a radio network instead of a slow satellite link. And it turns out that satellite links actually take quite a while for a receiver to get a fix of a location. So now having these known base stations speeds up your location by quite a bit. So we can get what we know now as a pretty accurate and quick location on our phones. Is GPS perfect? Not quite. Bad weather affects GPS signals. Make sure you make a note of that. A lot of people don't think about that, but you are looking to a satellite. So if you have really cloudy skies or rain, that can actually completely impact your GPS signal. It also doesn't penetrate solid walls or structures. So if you have a building in the way, and as buildings get taller in cities, GPS locations can be really difficult to get because you don't have that high geometric dilution of precision. And GPS signals or devices are often battery hungry, like your phone. If you're constantly using the GPS at your location, you'll notice your phone dies much quicker because it consumes a lot of battery to run your GPS device and get those signals. So those are some things that make GPS not perfect, and also it can send you in the wrong direction at times. But that may not be the GPS's fault. That might be the navigation software. So that gives you a little bit of information about GPS, and hopefully that gives you all you need to do to move forward from here.